Hello, wonderful physics kids. Mr. Johansson here. We're going to be going over Mechanics 11, which is non-perpendicular vector addition. This gets a little challenging. We are going to put a method on how to solve these. Every single step we do are simple, easy steps, but there's so many of them that we could get completely lost with this. So bear with me. I'll show you the method. It's a really good method. It works beautifully, and it's sort of good physics in that so often physics is really keeping good track of all of the little details and not letting any little details slip by us. So this is how we're going to do it. We have mechanics number 11. Oh, look at the quote first, huh? Henry Louis Mencken said, "The public demands certainties, but there are no certainties." Why did I put this? The great public would like to know that everything is okay. They would really like to know that. But in order to find out if everything is okay, you have to look ahead of you, ahead of the whole process of society. We have to be able to look a year, 2, 10 years ahead of us. So what do we use to look ahead of us? Do we use our intuition? Do we think about it? Do we have any other tools that we could use? Well, how about science? How about science? Science can shine a light ahead of you, give you an idea of what's coming, and let you take alternative measures should you not like what you're seeing. To deny science, when science is clearly showing you what's coming, and then you don't like what's coming, so you deny science instead of taking appropriate action, that's a recipe for disaster. I point out climate change. Climate change is significant. Climate change is really happening. Science is very clear, shining the headlight ahead of us, that climate change is the significant issue of our times. And yet there are people that are trying to deal with climate change by simply denying it, turning the headlight off. That's a recipe for disaster, because climate change is coming, whether you accept it or deny it. But if you accept it, you can take steps to change what's coming. If you don't accept it, anyway, let's move on and look at this mechanics number 11. This is mathematical vector addition. Mathematical vector addition. So let me put some problems up on the board, or some vectors up on the board, and you can take a look at what you think. So if I'm going to do some vector addition here, and I'm making up my own problem, I might want to just adjust how I'm doing it by making a sketch. So how about if I add one vector down this way? How about another vector up this way? And then my third vector that way. Okay, see what we get when we add those. Now I'll just put numbers to them. So this vector number 1, I'm saying is 10 newtons at, I would say that's 210 degrees. Vector number 1. Vector number 2 is 8 newtons at 340 degrees, and vector number 3 looks to be, I'm saying, 6 newtons at 125 degrees. Okay, so we have our 3 vectors we're going to be adding. This method is very straightforward. The basic idea of it is straightforward. Take a look at this. First rule: break each vector into x and y components. All right, break each vector into its basic x and y components. In other words, you could take an x value and a y value and construct any other vector. Similarly, you could take any other vector and break it down into its basic x and y values. Remember the number line. Right is positive, left is negative, up is positive, down is negative. Got to keep very close track of the positives and negatives. 2, we're going to just add those x and y values. Again, paying attention to the positives and negatives. And 3, we're going to use that to make new vector and measure it. That's all. That's all we're doing with this entire method. So, let's break each into its x and y components, shall we? All right, I don't need to make this really nice and neat. I just need to reference it, and I need to make sure I have a way of checking the angles a little bit. So I scale things somewhat properly. So 210 degrees, well that's 270, this is 180. So 210 degrees is over something like that. That would be 30. What would this angle be? 60 degrees. Key to this method, drop all vectors to figure out the right triangle. Always drop to the x-axis. So this vector is made up of a combination of this vector, the negative y vector, and the negative x vector. Okay, and this is my 10 newtons. Okay, I'll label that vector 1, important. Vector 2, 8 newtons at 340 degrees. Well, 340 degrees would be over here. I have 8 newtons. I am dropping to the x-axis, so that is now going to be made of the negative x and a positive y. 8 newtons. What is this angle that I have in here to complete the right triangle? Well, if that's 340 degrees, I'm going from 270 up to 340. I would think that you got 70 degrees for that. That's what I got. All right? And our third vector, 6 newtons at 125 degrees. Well, this is 90 degrees here. So that would be a 35-degree rotation down from that. 6 newtons dropping to the x-axis. All right, that's going to be negative y and positive x. And if it's 125 degrees, this is 35 degrees right here, 6 newtons. You got all that? All right, so now we're going to take data from this, and we're going to have to import it into a table. We've got to make up this table very, very carefully. So let's go to the other side and make up the table, shall we? So if you're following along, I would recommend you have all of that written down. And now, come on over to the other side of the board, and we're going to make our table. Now, our table is a very, very simple table. The whole point of it is that we're able to very, very clearly show everything we're doing here and keep track of it. So, we start with x, y, vector 1. All right? We leave 2 columns in this table so I can write the formula I'm going to use and then the solution to that formula. All right? So we have vector 2 and vector 3. And then we'll total them right there. So, vector 1. All right? Make sure you label your vectors. Vector 1, we have x and y are both going to be negative. First and foremost, I want to be very clear that x and y are both going to be negative. So I have the negative in front of the formula, and then I have a negative for the answer. I'm not going to forget the negative. Yeah, it's important. All right, so I have SOHCAHTOA, and using SOHCAHTOA and solving for SOHCAHTOA, I have 10 newtons at 60, oh, I'm sorry, no, I have cosine 60 degrees times 10 newtons. That will give me the x value. The y value would be the same thing, but sine of 60 degrees times 10 newtons. All right, and I'll solve that here when I get to that spot. Vector 2, I have the cosine. Oh wait, before I do that, positives and negatives. Y is positive and x is negative. Okay, so I take care of that. Now I have the cosine of 70 degrees times 8 newtons. This is going to be the sine of 70 degrees times 8 newtons. The third vector is x is positive, and y, we're going down, y is negative. So we have the cosine of 35 degrees times 6 newtons, and this is the sine of 35 degrees times 6 newtons. As long as I have my positives and negatives, this all will work out nicely. So let's jump to a solution, shall we? So 60 cosine times 10, all right, I'll use a slightly different color here for the solution sets. This would be 5 newtons. Cosine of 70 times 8 newtons, that's negative 2.7 newtons. And 35 cosine times 6 newtons is, that's going to be a positive 4.9 newtons. Why don't I add these up while I have this right in my calculator? So I have 4.9 newtons minus 2.7 newtons minus 5 newtons. That equals negative 2.8 newtons. That's my answer for my x value. Let's do y. All right, 60 sine times 10. That's negative 8.7 newtons. 70 sine times 8. That's positive 7.5 newtons. And 35 sine times 6 newtons, that is negative 3.4 newtons. So let's add these up. So I have my negative 3.4 newtons plus 7.5 newtons minus 8.7 newtons. And that gives me negative 4.6 newtons. Okay, so that is my solution then for the y-axis. All right, so now I have added up my x and y values. Well, now I have a value for x, now I have a value for y. What do we do for that? Let's put it on the other side. All right, so we're back to where we were. And now we need to make a new xy axis and finish this problem. All right, so I have a value for x, I have a value for y. I make a new xy axis. Well, do I have to do that? Where am I going to be focused? I don't need to have all 4 quadrants here. I have negative x and negative y. Negative x, negative y. So it really looks like I am right in the 3rd quadrant here. So I could do that, right? Have it nice and big, make it easy to work with. Always write big when you're working on these problems. Small will really mess you up. So x is negative 2.8, all right? 2.8. Notice I'm not saying negative because I already did it to the left. Got it. And 4.6 on the y. All right, so down 4.6 newtons. Now notice, I'm not measuring anything out, but I am drawing them so that 4.6 is clearly a lot bigger than 2.8. This will help make sure I understand the answers I'm getting. And if I do anything wrong, it should show me what I'm doing wrong. So our final answer is going to be this. That's the resultant. How do we find out what the resultant is? Well, for the magnitude of it, we're just going to do Pythagorean theorem. So I have 4.6 x squared plus 2.8 x squared equals, don't forget to hit equals, take the square root, 5.4. Does that seem possible? Yeah. 5.4 newtons. All right, what is this angle then? How do I get that angle? Well, I have this data, and this data is less derived than that data, so I should be using that. So if I take tangent of theta equals opposite over adjacent. Opposite, 4.6 newtons over adjacent, 2.8 newtons. 4.6 divided by 2.8 equals, and then I press second tangent, I end up with theta equals 59 degrees. Okay, 59 degrees. Is that our answer? Well, that's the answer for in here, but remember, straight up is 0 degrees. That was 90, this is 180, so I have to relate it to something here. Well, I have this angle. Can I take 270 and subtract 59? That would work. That's 211 degrees. So this is coming off at 211 degrees. So my final answer is 5.4 newtons at 211 degrees. That's how you do that. That is how you do this whole problem, okay? There's only one other bit that we need to talk about, and that's the equilibrant. What we have solved here is the resultant, right? This is the resultant. So what's the equilibrant? The equilibrant is what you would need to balance out the resultant. If all these forces were acting on something and you want there to be 0 force, bring it to equilibrium, the equilibrant, blue, would be equal and opposite. I don't have room to draw it up here on the board, but the equilibrant would be equal and opposite to the resultant. So if I have two people pulling on ropes at some angle to each other, well, the resultant of that is a big vector out that way. If I were to grab the rope and pull back this way and we're all not moving, I must have just applied the equilibrant to their resultant. That's all. So this was Mechanics 11. There's a bunch of problems for you to do. It's an important method to learn. It will really help you see how one vector breaks into a bunch of others. That's all. Thank you so much for watching. Have a great day.